Hello and welcome to today's virtual seminar, Water Activity 101, The Basics. I'm Brady Carter, a research scientist here at Decagon Devices. And today in this virtual seminar we're going to talk about basically what water activity is. We're going to give a description of it, a definition of what it is, and we're going to talk about how to measure it, and we're going to talk about how it's different from moisture content, and then go over some brief applications. And this is in preparation for a series that we do. We also have a Water Activity 201 where we talk about chemical stability, and then Water Activity 301 where we talk about physical stability. And the purpose of these and breaking them up into three parts is so that we can go into a lot more detail on about each of those subjects in terms of application. So today's seminar will be focused on the background of water activity and defining what it is, and not so much on applications. So if you're interested in applications, then I would strongly urge you to check out our Water Activity 201 and Water Activity 301 series. So just briefly going over the objectives for the virtual seminar today. First we'll start with defining what water activity is and how it's different from moisture content. We'll then go through and compare and contrast water activity and moisture content to make it very clear how those are different and what each one measures and how they're related as well. Then we'll talk about how to actually measure water activity, how the techniques that can be used to measure water activity, as well as strategies that you can use to make sure that you're getting the most accurate water activity measurements that is possible. And then we'll spend some brief time just an introduction to the various applications for water activity in preparation again for Water Activity 201 and 301. So to start out with, give an overview of the differences between water activity and moisture content. Let's start out with moisture content. Briefly, moisture content is a quantitative measure of the amount of water in a system. In other words, it's how much water is present. And it's usually reported as a percentage. So 100% would mean that you've just got water. 20% means that of all the materials in that product from a quantitative nature is water. And so typical ways of doing this is just to measure what the weight is when it's wet, then dry it out, take all the water out, and then weigh it when it's dry and see what the difference is. That's water. And then from that you can get a percentage, what percentage of the entire material was water, and then that's your moisture content. It's a concept that's pretty well known, universally known, used routinely in food manufacturing and pharmaceutical manufacturing, as a way of being able to look at moisture in a product as a standard of identity that gives an indication that that a product is what it's supposed to be, and that you're buying what you expect to buy as opposed to buying water. So this is an extensive property, and what that means is that it is dependent upon the material. The measurement of it itself depends on tracking the amount of material that's present. Water activity, on the other hand, is a measure of the energy status of water as opposed to a quantitative measure of the amount of water. This is a qualitative measure of the amount of energy that water contains in comparison to pure water. So while moisture content measures the amount of water, water activity tells you what the water's doing, what is its energy, how available is it for things to happen in the product or in the system. So this is an intensive property that doesn't depend on the amount of material for the measurement. In fact, you don't have to have a certain weight when you measure water activity, because it's dependent upon the energetics of the sample, which we're going to talk about how we measure that through something called vapor pressure. So water activity defined is a measure of the energy status of water in a system. And this is opposed to other definitions that you may have heard associated with water activity, which is that it's the amount of free or available water versus the bound water. And those terms get used a lot with water activity, and sometimes they can be quite confusing, and that's why we try to steer away from using those terms anymore, because they mean different things to different people. They aren't scientifically defined what is free and what is bound. That can have a reference to a quantitative measure, or it can have reference to a measure of energy. So it can be quite confusing. So we use instead the terms energy status of water in a system. How much energy does the water have in comparison to what it would have if it were pure water? And as the water activity goes down and it goes to lower energy, then it is true that it becomes less available because its energy is much lower, it's much more tied up, it's much more stable, it's not available for things to happen. It's chemically interacting with different materials either through hydrogen bonding, through ionic bonding, or through capillary effects. Its energy is being reduced, or through solute effects. And so we focus in on what the status of the water is as opposed to trying to somehow determine a level of free water. And often people make the mistake of saying that if you have a water activity of, let's say, 0.30, that means that there's 30% bound water and 70% free water. But that's not true. That's not a true statement because this isn't a quantitative measurement. It's not an amount of water. It's simply a relative status or a relative amount of energy compared to pure water. So a water activity of 0.3, it is correct to say that water in that system overall has 30% of the energy that pure water would have. So that's a correct statement, but it's not correct to say to make statements about free or bound water because that's not a quantitative measure. And in fact, there is an ASTM standard for measuring free and bound water, which is a quantitative measurement. You take a product and weigh it when it's wet, and then you centrifuge it or squeeze it and release water that's being held physically, and then weigh it again, and the difference between that is called the bound water. The free water. So that's a physical restriction of water, not a chemical restriction of water, or it's not a reduction in energy, it's just a physical impairment of water being able to move. And this is often called water holding capacity. So it's, in that sense, you could say that system could bind a certain amount of water. But it's just a physical restriction, like what a gel system would do in a product, or a fiber system, and where you physically restrict the water, but this water's still there, it's still very high energy, its water activity can be still quite high. So we focus on this statement that water activity is a measure of the energy status of water in a system, and this comes from the second law of thermodynamics, rooted in thermodynamics, this idea of looking at energetics. Thermodynamics tells us whether things are going to happen spontaneously because it's energetically feasible for that to happen. Kinetics tells us how fast that's going to happen, so this is a thermodynamic measurement of the relative amount of energy of a material and tells us something about how readily things are going to happen in a system. And it comes from Gibbs free energy equation, which tells us that if we want to know something about the energy of water, we need to look at how readily it escapes into the vapor phase. This is something called fugacity, and that's represented by F over F naught. F being the fugacity of the material, F naught being the fugacity of pure water. And as part of the requirement for being able to look at water activity as a thermodynamic concept, we have to identify a standard state. So in this case, the standard state will be pure water. So we're going to compare everything to pure water in terms of looking at what its energy is. So if we want to know how different the energy of a material is compared to pure water, we're going to look at how different is its fugacity. And fugacity references the escaping tendency of any material. So again, back to this idea of Gibbs free energy, if we want to know something about the energy of water, then we need to know something about how readily it escapes into the vapor phase. Things with more energy it's easier for them to go into the vapor state. They'll build a pressure when they go into vapor state if you're in a sealed system, and they'll exert a certain vapor pressure. So to get to this term fugacity, this escaping tendency, under most types of conditions, what we can do is measure what the vapor pressure is. So that's P over P naught. So the P is the vapor pressure over a sample, P naught is the vapor pressure of pure water, measured, both of them measured at the same temperature, and that is water activity. So as the energy of the water goes down, so will the vapor pressure above that sample will go down, because the water in the system has less energy, it's less able to escape into the vapor phase, it exerts less pressure, so its vapor pressure drops. And then if we compare what that is relative to what the vapor pressure of water would be, which is being dictated completely by the temperature of the environment that it's in, then we have water activity. And then we have some information about what the relative level of energy is. As a note, water activity is also sometimes reported as equilibrium relative humidity in a percentage. And these are the same values, just one of them's, the equilibrium relative humidity is just the same as the water activity, just divided by 100. So it can be reported sometimes on a percentage basis. And most people are familiar with the term relative humidity. It's something that we hear about in terms of the weather, and it affects how we feel, how the weather feels to us. But in this case, we're talking specifically about equilibrium relative humidity. So our surroundings have a relative humidity associated with it, which is being dictated by what the vapor pressure is and what the temperature is. But in a sealed system, when you can come to equilibrium, and when we talk about equilibrium in a sealed chamber, what we mean is that there's an equal, over time, there isn't no net change in the number of water molecules that are in the vapor state. So water molecules are constantly moving into the vapor state and then back in and condensing back into the sample. But over time, if you're at equilibrium, every time one goes in, one comes back out. So there's no net change in the number. So that's what we mean by equilibrium. Well, if you create those conditions in a sealed chamber and you're at equilibrium, then if you just measure the relative humidity of the head space, that's equilibrium relative humidity, and it's the same as water activity. So while this room has the room that we're in has a relative humidity associated with it, it doesn't have necessarily an equilibrium relative humidity because it's not a sealed system. So it doesn't have a water activity. But that gives us some indication of how you might measure water activity. If it's the same thing as relative humidity, if you were to take a relative humidity sensor and put it in a sealed system where you've reached equilibrium and you take a measurement of relative humidity, you've got water activity as a method for being able to do that. Moisture content, as we outlined earlier, is a quantitative measure of the amount of water in a system. And what's important to note about moisture content, we tend to think of this as a fairly simple concept, moisture content, but when you start to actually look at the measurement itself and think about what the implications are of this measurement, and you start to think about how to get repeatable results, then it starts to be fairly complicated. And one of the hardest things about moisture content is that it's an empirical measurement. There is no standard that you can compare your performance of your particular method to make sure that it's accurate and doing what it's supposed to. Unlike water activity, and as we're going to find out when we talk about water activity measurement, there are standards available for water activity. If you make up a salt solution to a specific concentration, then you know what the water activity is based on thermodynamics. It tells us or dictates what the water activity will be of that binary solution. We don't have that kind of an advantage in measuring moisture content. You can't take a material and add 20 grams of water to 80 grams of material and say it's 20% moisture, because moisture in isn't always moisture out. Some moisture gets and becomes a permanent part of the sample. So you can't say that's 20% moisture and then try to make it as a standard. And plus, if we look at a comparison between, if we look at the water activity scale, which goes from basically from 0 to 1, 0 actually is not a real condition that can occur, which is why we have a hard time figuring out what dry is. We don't have any kind of scientific definition of dry, which makes it difficult to measure moisture content. But if you look on the water potential scale, which is the same thing as water activity, a water potential of water is 0, and then it goes up exponentially with no end. So that means there is no actual 0 point when we talk about water. So it's impossible to, from not having a 0 point, to then have some sort of a standard to be able to compare moisture content to. So it's truly an empirical measurement. All you can actually calculate for moisture content is precision, not accuracy. And precision, of course, is how closely are your measurements together. Why accuracy is, did you actually hit the bullseye? If you don't know where the bullseye is, you don't have any way of knowing if you've hit it or not. So it's not possible to actually report an accuracy for moisture content measurements. Even though it's reported all the time, it truly isn't possible because nobody knows what the right answer is. And so that's a challenge for moisture content. What it results in is the really a very difficult time in being able to have reproducible results with moisture. Now, you can get repeatable results. And what's the difference between that? Well, repeatable is within one facility using the same method and getting the same results over and over again. Reproducibility is comparison between multiple labs using possibly different methods and trying to get those to match up. And that's very difficult without a standard to be able to somehow manage to do that. And so the result is that depending on the method used, the answer for moisture content can be widely varied depending on what the method is that's used. In fact, for some types of samples, there's been standard programs where a sample's sent out and everybody measures moisture on it, and the results will come back anywhere from 8 to 18% moisture content. So it makes it very difficult to try and do any kind of comparison between different facilities. So at the end of the day, all you can hope for is to be repeatable in your facility, so that at least you know if the numbers change, then something's happened and something's not right. And then it does still provide you with that standard of identity. But the take-home message here is, don't think too much of what your moisture content measurement is telling you. It provides some very basic information about the quantitative amount of water. Keep in mind that the goal for every kind of performance in moisture content should be focused on getting the same results again and again. Now that said, there are two primary ways of measuring moisture content. One is loss on drying, and this is based upon Fickian diffusion of water through evaporation out of a sample. You weigh it wet, you put it in an oven under elevated temperature conditions, creates a low vapor pressure inside that oven, and so evaporation occurs out of the sample. The rate of that is being dictated by the sample itself, so different materials will take different amount of times to dry. Then you take the sample out after it's dried out, you weigh it dry, the difference between that dry weight and the original wet weight, that's water, and then you divide that either by the wet weight or the dry weight. And that's important because there's two different ways that you can report moisture content, on a wet basis or a dry basis. And the two can't be compared to each other, they have to be transferred or manipulated in order to make comparisons between them. So it's important to know which method that you're using. Now, one of the problems with loss on drying, when you put something in at elevated temperatures, things other than just water will evaporate out. And hence we use the term moisture content as opposed to water content. Moisture being roughly defined as anything that evaporates out of the sample at the given method that you're using or at the given temperature that you're using to evaluate that. So things other than moisture very definitely will come out of that sample. In an effort to try and alleviate those issues, then we go to something called titration, which most commonly is a Carl Fisher as the most common titration method. And in this method, the strategy is to avoid the problems of things other than moisture evaporating, so instead you use a reaction that involves water so that it's very specific to water. And then by tracking some other material that's involved in the reaction and its use, depending on how much of that you use, in most cases that's iodine, you can relate that directly to how much water is in the system based upon how much iodine you use, and then the end of the reaction is indicated usually by a change in the electrical properties of the solution. The problem with Carl Fisher, though, even though it is more specific to water, if you don't use the right combination of solvents when you're creating or using this test, if you don't solubilize out all the water, you won't see it all, and so you can still have mistakes made for moisture content analysis. So take-home message is moisture content may not be as simple or easy as it first appears to be able to get good, reliable results. Now to try and solidify a knowledge of the difference between moisture content and water activity, we're going to talk about a little experiment that you could easily run in any laboratory. First part of this experiment, or step one, is to take a cracker, and this would be something like a saltine cracker. It's got it's very stiff, it's got a snap to it, very low water activity, initial water activity of about 0.2. And we're going to take that and put it in over an excess of sodium chloride, saturated sodium chloride. And at saturation, sodium chloride has a water activity of 0.753 at 25 degrees C. If we have an excess in there, then the cracker has no choice but to take on moisture, because the conditions inside that sealed chamber are going to be at a water activity of 0.753. So it will take up water until it comes to a water activity of 0.753. And at that point, that cracker has now become very soggy. It's lost its texture. Certainly wouldn't be something that would be desirable to eat. So if we diagram what that would look like, so over time, our cracker is going to move from a water activity of 0.3 to a water activity of 0.75. And in that process, its moisture content will change from 4% to 20% moisture, and it will be a very soft, mushy mess. If we, in a different container, if we take fresh cheese, and fresh cheese is a very soft product, it's very high water activity at about 0.92 starting out. If we take that and put it in a sealed chamber, again with an excess of saturated sodium chloride at 0.753, in this case, the cheese has to actually lose moisture to the system or to the saturated slurry, because its water activity is higher than 0.753. And water always moves from high energy to low energy. So this cheese will lose moisture, and if we diagram that, it will move from a water activity initially of 0.9 to 0.75, and then it will stop and it will come to equilibrium with the conditions inside that chamber. And in that process, it will lose moisture content going from 60% to 30% moisture. Now this cheese is a very hard, very stiff product. Again, not something that you would actually want to consume. Now the question is, if we were to take an equal amount of our cracker that we've pre-equilibrated and put it with an equal amount of our cheese that we've equilibrated, what will happen if we put those in a sealed chamber together? So we've got a 20% moisture cracker and a 30% moisture cheese. Which way will water move in this situation? And this is actually somewhat of a trick question, because it's not dependent upon the concentration of the moisture in these two products. They have different amounts of water, but if you remember, we have equilibrated both of them to 0.75 water activity, which means their water activities are the same. So the correct answer to this question is that water will not move. And the reason it won't is because the energy of the water in the cracker and the cheese is exactly the same. So there's no motivating force for water to move. It will not move from one to the other because the energy of the water is exactly the same. Even though they have different concentrations or amounts of water, the energy of the water is the same. So it's water activity that dictates moisture migration between different materials, not moisture content. If you try to match up moisture content to prevent moisture migration, you'll have a disaster on your hands. So it's water activity, it's the energy of the water that dictates that, not the amount of water. So in summary, this comparison between water activity and moisture content, water activity is a measure of the energy of water, while moisture content is the amount of water. Are there standards available? For water activity, yes, we can use salt solutions at specific concentrations. For moisture content, there is no standard, it's an empirical measurement. The cost of these units to measure water activity and moisture content, pretty similar. Water activity instrument, desktop instrument, runs about the same as a moisture balance would run. But there can be differences too. If you go into NIR for moisture content, then you're going to get up into the 25-30K range. And if you just buy an oven and a balance for doing moisture, then you probably aren't going to spend that much. But again, it's very labor intensive to do that. The reporting methods, water activity is a unitless measurement. It's relative scale, so we use water activity units. Moisture content is reported on either a dry or a wet concentration basis or percentage. The methods for water activity, there are 5 different methods for measuring water activity. AOEC lists 35 different methods for measuring moisture content. Sample preparation, pretty similar for the two, depends on the material that you're using and the method you're using. One of the big differences is that water activity is a non-destructive test. So we've contrasted water activity and moisture content, but they actually are related to each other, which makes sense that if you have more water in a system, then the water is going to have more energy. And they're related to each other through something we call a moisture absorption isotherm. And a moisture absorption isotherm tells us how much or how water is absorbed by a product at a given temperature, isotherm meaning one temperature. And you do have to do this relationship at a certain temperature because the relationship between water activity and moisture content will change with temperature. And there's a couple of things to note about these relationships. First of all is that it's not a linear relationship. It's not a one-to-one relationship. As you change water activity, you change moisture content. And the relationship itself will actually depend on the range of water activities that you're looking at. The other thing to note is that it's very unique to each type of material and being dictated by the ingredients or the matrix that you're dealing with. Some types of matrices can hold lots of water at a given water activity, while others can't hold very much at all. And a good example of this would be something with a high level of sugar in it. Can hold a lot of moisture, at a given water activity. And if you were to compare directly with something that had high fat content, it would not be able to hold very much moisture at all because it's hydrophobic. It doesn't have any hydrogen binding sites. It doesn't have anything in there that wants to interact with water. So just a small amount of water equals a large amount of energy. Versus something that has sugar, where lots of water can interact very easily with or loves to interact with that sugar through hydrogen bonding, and in that process it lowers its energy, so you can have more moisture for a given energy in something that has a high sugar content. So the shape of this isotherm, again, is being dictated by the makeup or the matrix that you're dealing with, and it's unique for each type of product. It also provides some very valuable information about the material. It tells us how hygroscopic a material is. It can tell us about glass transition. It can tell us about how things are going to respond as they encounter different types of environments, or if they come into contact with other materials that are at different water activities. All this type of information is provided by these moisture absorption isotherms. Now let's talk a little bit about how you actually measure water activity. Water activity as a concept has been around for many, many years. And initially, before there was instrumentation available, it would be determined through calculations or models. If we look at Raoult's law, what Raoult's law tells us is that if you want to know the water activity, all you need to know is the mole fraction of water. Well, that works okay for ideal systems or very dilute systems, but it makes an assumption that there's no interaction between the solute and the water itself, which does not hold true in almost all cases. So Raoult's law doesn't really do a very good job of predicting it, and so researchers came up with alternate models that tried to account for this non-ideality that was existing as you got different types of interactions. And they would do those for specific ingredients and come up with some empirical models with constants that would change depending on what material you were using. And so from that we got these, the Norrish, the Grover models. And then the Ross equation is very useful because what it tells us is that if you know the water activity of all the individual ingredients, you multiply them all together and that will tell you what the final water activity is. And so this allows for being able to do a prediction of what the water activity will be of a recipe without ever having made that recipe. And that's why there's still use for these models. We have good instrumentation available today to measure water activity. So why would you need these models? Well, it gives the ability to do some food engineering work ahead of time before actually making a product to see what its final water activity would be, and will that be an acceptable water activity range. Of course they're not going to be exact, but they give you a good idea of the range that you're going to be in, and then you can make decisions based upon that whether or not that is going to be a feasible product to use with those models, or using those models to be able to predict that. You can also use them, and this is maybe even more valuable, if you have a given product and its water activity is higher than you want and you want to go to a lower water activity, but you don't want to have to dehydrate it anymore or drive out more water. Is there a way that you can actually do that? Well, these models allow you to determine what will the effect be if I added a higher concentration of sugar or a higher concentration of salt, and calculate ahead of time exactly how much of those materials, what concentration you'll need to add in order to achieve your desired water activity. So that you can do that without doing the cook and look process of just adding different amounts and see if it works or not. So it saves a lot of time from that standpoint. But at the end of the day, you're going to have to actually take measurements with some sort of reliable instrumentation or method to be able to get the water activity. And over time, there's been essentially 5 different basic ways of measuring water activity. The fact of the matter is that we only actually deal with 2 of those today, and that's electric hygrometer and chilled mirror dew point. And the other ones have a lot of challenges associated with them that really don't make them feasible. Hair hygrometers, this was the idea here, was that hair properties change with humidity, and if you can calibrate that, you can equilibrate polymer material to your product, and then how much the dial moves based on the changes in its physical properties, link that up to water activity. And that would work, but unfortunately it takes about 2 to 3 weeks to do one test. So not really feasible anymore. Freezing point depression is the reason why we salt the roads in the winter. As you lower the salt lowers the water activity. As the water activity is lowered, so is the melting point or the freezing point. And so ice will suddenly melt if its water activity has been lowered by the addition of salt. So if you can figure out how much the freezing point has been depressed or lowered, you can link that up or correlate that to a water activity. because as the energy is lowered, so does the freezing point lower. But again, this is very difficult to do. It only works for very high water activity samples, so not really a feasible way. Isopistic equilibration was equilibrating your sample to a sample that had a known moisture absorption isotherm. When the known sample, it equilibrated to your sample, you could measure moisture content, then through the isotherm get the water activity. So a very backwards way, again, takes a long time to get water activity values. So basically we're left with electric hygrometers or chilled mirror dew point instruments. And electric hygrometers are a secondary way of measuring water activity using an RH sensor, as I described earlier. If you create a sealed system and you're at equilibrium, if you measure the water relative humidity of the head space, then that gives you water activity. So it's a secondary way based upon the polymer, which is the RH sensor, and its electrical properties and how those change and respond to changes in relative humidity. And then we have the chilled mirror system. And this is the system that's utilized by Decagon for our benchtop instruments. And the reason why we use this system is that it is a primary method for measuring water activity. And the reason why it's a primary method is we actually directly measure the vapor pressure inside that chamber over that sample, and then compare that to the vapor pressure of pure water. We get the vapor pressure of the sample using a chilled mirror, and we chill that mirror down until the point at which dew forms. So we're down below the dew point temperature. And we measure the temperature that dew forms, and that's the dew point temperature. And using that dew point temperature, we can calculate what the saturated vapor pressure is of the chamber at the dew point temperature, which is equal to the partial pressure or the vapor pressure above the sample. So by chilling that mirror and figuring out the dew point, we can determine what the vapor pressure or the partial pressure is. That's the numerator for our water activity. Then if we measure the sample's temperature, from that we can calculate what the saturated vapor pressure is, or the vapor pressure over pure water, which is our denominator. Now we have everything that we need to have water activity. So that's how this method works. It's a very fast method because we don't rely upon equilibration of a sensor, an RH sensor, to the chamber. And the time constant of that equilibration for other systems that utilize RH sensors is quite long. It'd be up to 40 minutes to be able to get full equilibration. And so that they take much longer. The reason why we can do it much faster with our method is because it's a primary method where we're not reliant upon equilibration of some sensor to the conditions. Also, that sensor has to be thermally equilibrated to the sample in order to get good measurements. So because we're not waiting for those things to happen, all we're waiting for is vapor equilibrium, which for many types of samples, and this again depends on the diffusion properties, but for many types of samples that's a very fast process, in just a matter of 3 to 5 minutes, and you get a test measurement. And that's why we can do it so fast and still have a very high level of accuracy at plus or minus 0.003. So it's a very advantageous from that standpoint to be able to use this type of method. Now there are a few disadvantages to the chilled mirror. One is that you got to keep the system clean. If the mirror or the infrared sensor are contaminated, then they can give erroneous readings because they're not measuring properly the sample temperature or the dew point temperature. In addition, there are certain types of low molecular weight alcohols and volatiles that can interfere with these measurements. And they have to have certain properties associated with them, very specific properties, in order to interfere. And that's things like ethanol and propylene glycol, butanol. They have these properties that allow them to co-condense on the mirror and then prevent water from being able to get back off the mirror, which causes further readings on that mirror to be erroneously high, which means that if these materials are present, the instrument will give too high of a reading for water activity. And we have created ways of being able to overcome this through the use of again, the RH sensor that we talked about. So we do have to go to a secondary method for these specific types of materials. But our system has, our benchtop instrument has that sensor built right into it, so it's just a menu selection to go between the two. For everything that doesn't have that, you would certainly want to use the chilled mirror. It's faster and it's more accurate. Just briefly, I want to talk a little bit about the possibility of being able to do both water activity and moisture content in one instrument. And we do have a system to be able to do that. It's called the Aqualab Duo system. And the way that this works is that if you do know the isotherm, thinking back to that relationship between water activity and moisture content, if you know what that relationship is for a given material, and again it's going to be unique to each product or material, then you can create a model or an equation for that isotherm where you can take water activity that's measured off our instrument, plug it into that equation, and then get a prediction of the moisture content. So this is a secondary predictive method for moisture content, much like NIR, if you were to use NIR to determine moisture content, which determines moisture content based upon the adsorption or reflection of near-infrared radiation. In this case, though, we're using a direct measurement of water activity to then predict what the moisture content is. So this, again, this must emphasize this is going to be specific to each product. So you have to have a calibration for each product in something like NIR. You have to have a specific model for each product that you want to analyze. So this is meant to be a system for a QA, QC, where everything's being made the same all the time and you just want to track moisture content over time. This gives the option of a less than 5-minute test, and plus you get your water activity, which gives you the helpful information about the product's shelf life and the stability of the product. But you also get your moisture content that you can have for labeling, nutritional labeling, and for standard of identity and for reporting. So it's a time-saving process, and it works very well for products that are dry to intermediate moisture. It doesn't work well for high moisture types of products, so there are some limitations to where you could actually use this system. But if you're interested, you've got to measure water activity anyway, why not get moisture content at the same time? Certainly contact us here at Decagon and we can talk to you more about the possibility of that application for your particular situation. Now talk a little bit about making accurate measurements of water activity. So the most important concept to understand in order to get accurate measurements is the use of our verification standards. Again, these are salt slurries. You can use both saturated and unsaturated. We use unsaturated and sell unsaturated here at Decagon because they're easier to handle and to deal with. They come in single-use vials. You simply put them in a cup, stick them in the instrument, and measure the water activity. It says right on the vial what the water activity of that solution should be. If the instrument doesn't read it as it should be, or what the value that it should be, then you know that something's wrong with the instrument. It's not performing the way that it's supposed to. So immediately there's steps to take to be able to overcome that. We have standard operating procedures that we provide of things that you should do, steps you should take if those verification standards don't read correctly. First thing to do is to clean it, make sure it's clean, as I inferred a couple of slides ago. If it's not clean, then it can affect the readings, and that's most often the issues that we encounter with customers who can't get their verification standards to read correctly. They just simply need to clean the instrument. And we have videos available from our website about how to clean the instrument and clean it properly to try to alleviate these problems. And in most cases, you can overcome any issues just simply by cleaning. Now, there are situations where a permanent offset has occurred, and so we have built into the system the ability to use these salt standards to make a linear offset to the system. And in extreme condition or situations, then you might want to send it into us, and that we can make any kind of repairs that are necessary. Another important factor to consider in getting accurate measurements is the temperature of the sample. Water activity is temperature dependent, and so our instruments, our benchtop instrument, our Aqualab 4TE, is temperature controlled for that very reason, to try and avoid the problems that can come from ambient temperature switching all the time, lab conditions changing. If you have a temperature controlled instrument, you set it to say 25 degrees C, and then all of your tests are at 25 C, so temperature isn't a factor. However, if you bring a hot sample into a cool instrument, so something at maybe 35 degrees into an instrument set to 25, then you've created conditions prime for condensation. And so the instrument will come up and tell you the sample's too hot, but you also need to check inside the instrument to see if you've condensed water inside there, because certainly that will affect subsequent measurements. Another way of affecting the accuracy of measurements and the repeatability is through the sample preparation that's used. And we're embarking right now on an extensive study where we're figuring out the optimal water activity testing procedures for different types of samples. And each sample is somewhat unique in how it needs to be handled. A lot of that you can figure out as you work with your products and you measure for water activity, and you come up with some sort of a standard procedure for sampling that gives you consistent results that you can rely on. But we're also doing that investigation, and we make those results available as we finish them through our website. So far we've done analysis on solids dosage tablets, on baby formula, and we're just finishing up on jelly beans. So as that information becomes available, we'll distribute that, and it will give helpful information specifically about those products and how to handle samples. But in general, whatever product you're measuring, first thing you need to do is have a representative sample that is representative of all the different components of a product. If you want to know what the overall water activity of a multi-component product is, you need to take through both components. If you want to know just each of the components individually, then of course you separate them and read them individually. So it needs to be representative of what you actually want to find out about your product. If you're going to slice and grind, and we don't recommend you do unless you have to get it to the size that will fit in the cup, or if you want to try to increase or speed up your test times. Slicing and grinding will speed up test times in most cases. But if you've got a coating that's intact and you want to know the water activity with that coating intact, then certainly slicing or grinding is going to destroy that and makes it so you can't make that measurement. Plus the grinding process can dry out, it produces heat, and it can actually dry out the sample. So the important thing is that if you're going to do slicing and grinding, then just be consistent. Try to make it so that that's not a source of variation in what you're doing. And then the other important thing is to try and prevent moisture exchange with the environment. Some types of samples are very sensitive to exposure to the environment. They'll change their water activity from their current water activity to whatever the water activity of the environment is, or the relative humidity of the environment, in a very short amount of time, and that affects the readings. And so you should limit the amount of time that your sample is exposed to the environment, and you can do that through the use of the lids that come with our cups. They'll serve as a decent moisture barrier for a short amount of time. Certainly you don't want to store long term with just those lids in place. They aren't a perfect seal, but for a short amount of times from sampling into the instrument, then they can be very effective in limiting the exchange to the environment. And just now a quick overview of the instruments that Decagon provides for measuring water relations and water activity. We have up in the top left corner our portable instrument, the Pocket, meant for spot checking only, to be taken into a facility, and then you can do a spot check on water activity and see what that water activity is. This is not meant for high throughput quality assurance type of testing though. For that you would want to use the benchtop instrument that's in the top right corner. That's called our Aqualab 4 instrument. It's available in several different iterations, one that's not temperature controlled, one that is temperature controlled, the 4TE, and then a 4TEV that has temperature control and has both the chilled mirror and the volatile sensor if you have products that have propylene glycol or ethanol. Then we also have another additional version, and that is the Duo that I talked about, where it does both water activity and moisture content. Same instrument, it's just programmed to have those equations preloaded into it. And then we have on the bottom our brand new Aqualab VSA, Vapor Absorption Analyzer. This instrument's purpose is to create those moisture absorption isotherm curves that we looked at earlier. A traditional way of doing that was to use desiccators. Took a long time, months, to be able to collect that data, and you got very few data points for your effort. This will automate that whole process. It can run both a DDI and DVS isotherms, for those of you that are familiar with that. So that's either dynamic or traditional equilibrium isotherms, and automates the whole process and provides you valuable information. Those isotherms were very helpful for determining shelf life, looking at stability, evaluating different types of products, as we'll see in the application section. So that instrument's available as well. It's more pricey than the other two instruments, obviously, but still much less than what you would pay for most moisture absorption isotherms that are out on the market. Actually, all moisture absorption isotherms that are on the market. And now just a close-up view of the Aqualab Series 4TE. This is kind of the workhorse instrument that Decagon provides for measuring water activity. Many of you may be familiar or have used the previous model that Decagon sold, the Series 3. This had a drawer that came out. You put your sample in, close the drawer, and then turn the knob. Improvements that we've made with this system, we went to a clamshell design instead of the drawer. That makes it much easier to access the inner parts that need to be cleaned routinely. So you don't have to take the instrument apart to clean it. You just open the lid and you can access all of those important sensors that have to be kept clean. We added an O-ring seal, so the chamber's much more tightly sealed. That speeds up equilibrium and prevents drift over time. This, of course, the V model can incorporate a volatile sensor. It used to be you had to swap blocks in the old Series 3. Now you just use the menu and just do a configuration change. It is Part 11 compliant, has administrator settings and password protection. Again, this can be upgraded to measure moisture content with the Duo form. It does have onboard storage, so you can save test data. You don't have to sit and record every data point anymore. It can easily be downloaded to a computer with a nice program that interfaces with the system. Has the same accuracy and performance as Decagon's previous instruments have always had, and just adds these additional capabilities that makes it a very nice instrument to use. So if you're interested in finding out more about that, certainly contact us here at Decagon. And now to finish out, I'll just go over real quick, a brief introduction to different applications. If you want a lot more specifics on these, see our Water Activity 201 and 301, then we'll go very in-depth into each one of these subjects. But briefly, water activity is probably best known for its relationship to microbial growth or spoilage. In fact, it's incorporated right into the FDA food code for potentially hazardous foods. The definition for that is dictated by what the water activity is. And we've known this since the 50s by Dr. Scott's work, where he showed that each microorganism had a limiting water activity, where if you were below that water activity, they just couldn't grow anymore. And this was being controlled by water activity, not water content. In fact, the same water activity applied for the growth of organisms in all different types of systems, whereas they were trying to apply 12% moisture content being safe in one product to another product, and it would be a disaster, it'd spoil. And so based on that frustration, this work was done, and it was determined that what's really determining this growth is water activity, which makes sense considering that these organisms are existing in an environment where the water in its surroundings is at a particular energy being dictated by the water activity, while the inside of these organisms and inside their membrane will also have a certain water activity, and they are dependent upon passive transfer of water from high water activity to low water activity inside of their cells. If their water activity inside their membrane ends up being higher than the environment because of the result of lowering the water activity of the environment, they experience osmotic stress and they'll stop growing. So we can take a look at different organisms and see exactly where they stop growing. So gram-negative organisms stop growing at 0.91 water activity, gram-positive at 0.86. Yeasts, their practical limit's 8.8. Mycotoxin production stops at 8.0. Molds stop at 0.7. And then below 0.7, we call that the practical limit because between 0.7 and 0.6, all that will grow are osmophilic yeast and xerophilic molds. So if you've got your sample somewhere below 0.7, there's a pretty good chance that you're not going to develop any kind of spoilage over time. Now keep in mind that water activity, these are minimum growth water activity levels. These are not kill levels. Water activity is not a kill step. It doesn't kill microorganisms by lowering the water activity. In fact, many microorganisms, such as salmonella, can survive very well for an extended amount of time at low water activities. The difference is that they're not proliferating, they're not growing, they're not going to grow to levels that could cause an infection. So as long as they're present in levels below the infection level, over time for that product, you're not going to develop levels that are high enough for infection. But if you bring in an external inoculant in and inoculate that sample with a high enough load of microorganisms to cause an infection, then they will cause an infection. Even though their water activity is low. It's just that it won't grow on the product itself over time and then cause spoilage. So, and we have great examples of this. There's chocolate that's had salmonella survive in it for an extended amount of time. We've had peanut butter that's been recalled because an external source inoculated that peanut butter with high levels. The peanut butter itself was very low water activity, would never have supported the growth of anything to the levels to cause an infection. But it's important also in powders. You can have these organisms surviving in very low water activity powders. And you may think of, why would you ever measure the water activity of a powder? It's very low. It's never going to support microbial growth. Well, besides there being physical stability aspects that we'll show in just a minute, it's also important to know that powder is free of microorganisms. And there's an emphasis now on sterilizing these types of dry powders. Because if you have a microorganism present, and most times these powders are used ingredients, and eventually are going to go and be mixed into some sort of a product that could possibly be very high water activity, in which case it brings those organisms with it. They start to grow and proliferate in that high water activity situation or system that it's in, and now it's going to cause an infection and result in a recall. So there's an effort to try and figure out effective ways to be able to sterilize these dry powders, and it's very difficult to do that because they're at low water activities, and one of the things that you need for effective sterilization is humidity. There's a lot of work being done, research right now, and trying to figure out what is the optimal conditions for these dry powders to keep them free flowing, but also to get effective sterilization. And certainly water activity plays an important role in that. So what does water activity do to an organism? If we look at a growth curve for a microorganism, in this case we're looking at staph, keep in mind that the growth curve, the growth on the side is logarithmic growth, so each one of those is a 10 times difference. Notice that for water activity of 0.87, we've drastically increased the initial stage, where it's very short for higher water activities. The growth stage, the slope is much lower or smaller than it is for the higher water activities. And then the final stage is at a much lower value, below the infection level, as opposed to those at higher water activity. So there's almost a 20 times difference in the amount of growth higher water activities than there is at the low 0.87 value. It's also true that the water activity or the growth limit for an organism is being dictated by not only just water activity, but the other conditions that are existing for that particular product. And the water activity growth limits that were established by Scott were done so with all other conditions being optimal. So optimal for pH, optimal for nutrient level, optimal for temperature, oxygen availability, all those things were as optimal as they could be for the growth of that organism, and the only thing that was changing then was the water activity. So it represents worst case scenario. These are the absolute limits where the growth will occur. But in reality, an organism may stop growing at a higher water activity if you have combined effects of other factors, such as it been heated? Has it being refrigerated? Has the pH been lowered? What's the redox potential? Are there preservatives present? Are there competitive organism present? What are the vitamin availability and what is the nutrient availability? All of those factors combine together to determine whether an organism will grow. And this is called hurdle technology. And it's the precursor to what we know now as the HACCP programs, where a hurdle takes on the form of a critical control point. Where if you want to keep the product safe, if you put enough hurdles or critical control points in front of it, then you can prevent its growth. And sometimes that may just be water activity, as in number 3 example. Water activity in this case was low enough that it was a big enough hurdle to prevent the growth. But in the case of number 6, you needed both water activity and the effects of pH to stop the growth. The water activity on its own was not enough. So these different environmental effects work synergistically to determine whether or not an organism will grow. And in fact, this has been built right into the FDA's definition of potentially hazardous foods, where they're considering the interaction between water activity and pH as opposed to considering them each separately. It used to be either you had to have a water activity less than 8.5 or a pH less than 4.6 to be considered safe. But in fact, they work together synergistically so that you can have higher conditions for each and still be safe. For instance, in this case, for table A, this is where you have that you have a kill step, and you have that destroys vegetative cells, and then you subsequently package the material. If you have that process, then you can have a water activity of 9.2 or less, and regardless of the pH, be considered to be safe, potentially hazardous. You don't have to do time temperature control. If you have a pH less than 4.6, then it doesn't matter what the pH or what the water activity is, you're safe. But if you have a combination where you have water activity between 9.2 and 9.5 and a pH between 5.6 or 4.6 and 5.6, then you're still safe, even though you're higher than the lower limits for those individually. Because of their combined effects, that product's safe. Then there's table B. This is to use where you don't have a kill step, or you do have a kill step and you don't package, or if you just really want to be conservative and safe, these are the values to go with. And here now the water activity's moved down to 0.88. If your water activity is less than 0.88, doesn't matter what your pH is, product's considered to be non-potentially hazardous. If you're less than 4.2 on your pH, doesn't matter what your water activity is. But again, you can have interactions. You can be below or between 0.88 and 0.90 and still be safe, as long as your pH is somewhere below 5.0. So it's important to have an understanding of these two concepts, and then use these tables when you're manufacturing to determine whether your product is going to be considered safe by the FDA or not. So if you've established that you need a certain water activity, you've done that through shelf life testing to figure out this is the optimal water activity to get the desired shelf life. And again, we can help you do all of that in subsequent seminars. But it is possible to figure out what an optimal water activity to get the maximum possible shelf life for a given product. Well, what if you're not at that water activity? How do you achieve it? Well, you can formulate to get specific water activities and to at least control water activity. One of those ways is through dehydration, most common way. You cook it, you dry it to drive the water out and lower the water activity according to the isotherm. Sometimes you have to build edible films to prevent water from migrating and changing the water activity of different components. But maybe you don't want to alter it that way. You don't want to change the amount of water that's in there. How else can you lower water activity? Well, that's where additives become very helpful. And these are ingredients that you're going to put in that have the ability to bind water through either hydrogen bonding, ionic bonding, van der Waals forces, whatever the case may be. But they have the ability to be able to lower the energy of water just simply by being there or being present. So with the same amount of water still present, as you add these additives, which we call humectants, then they lower water activity. Even though you have the same amount of water, because they have places for water to interact, it lowers the water activity. And so some of the most effective humectants, and salt technically isn't truly a humectant, it's an electrolyte, but we'll just include this list to be everything that would lower water activity. But in this case, so for humectants, salt is one of the most effective humectants there is. It's very effective at lowering water activity. It also has antimicrobial activity in and of itself. But of course, if you add salt, your product's going to taste salty, and it adds sodium to your product. So there's things to consider when you start thinking about these humectants or additives that you're going to add to lower water activity. You can also use sugar. Simple sugars are very effective at lowering water activity, but they also bring a flavor or a sweetness to the product and increase the sugar content. Glycerol is a very common humectant that's used because it doesn't have necessarily the same flavor aspects or organoleptic issues that the others like sugar and salt would. And it also is completely miscible in water, so there's no limitations on solubility that come along with it either. Plus it provides plasticization somewhat similar to water, and so it can have some of the same properties of water without having the potential for microbial growth. So there are different choices for using for these additives. In general, the lower the water activity, the lower the molecular weight, the more effective it is at lowering water activity. So as you get to large molecular weight materials, big polymers like starch and gums, they aren't nearly as effective at lowering water activity as low molecular weight simple sugars are. So can you formulate a product that has multiple components and different water activities? If you do formulate that product, it's not going to be stable. It's going to exchange moisture until the water activities are the same. So it's more important that you match up the water activities, or it's essential that you match up the water activities. That doesn't mean you have to match up the moisture contents. And by looking at the isotherms, and this is an example of a snack cake that has three very distinct components, an icing, a cake, and a cream filling. If that's processed so that all of those different components have the water activity of 0.7, that will be a very stable product. There won't be any moisture exchange. But notice that each one of those components have a very different amount of moisture present at that given water activity. Some are high lipid fat content. They're not going to hold very much moisture like the icing. Whereas the cake has lots of sugar, lots of starch, lots of different materials that can interact with water, and so it can hold much more water at a given water activity than the other two components. So to be able to make this type of a product, you've got to have an understanding of what these isotherms are and what their interrelationships are and what water activity is going to do and how water activity has to be matched up to try and prevent moisture migration. Water activity is also affected by temperature, as we stated earlier. Now, different products react to temperature, their water activities react to temperature differently. So it's very product specific what this relationship is, and so as such needs to be established for any given product. But why do you need to know about the temperature effects? Well, many products will be processed at 25 degrees C and then be shipped in a truck that reaches temperatures of 35 to 40 degrees C. There can be a lot of temperature variability, temperature abuse for products. And what happens at those elevated temperatures? Well, your water activity may be safe at 15 degrees C or 20 degrees C, but then at 40 degrees C, as shown in this example, at 25% moisture content, you've now moved above 0.7. That product can suddenly be susceptible to mold growth where it wouldn't have been at lower temperatures, just simply because the water activity's changed. And the water activity inside of a package can change with temperature, even if the moisture content doesn't change, because you've got an effective moisture barrier. Because again, we're talking about the energy of the water, and that's being influenced by the temperature that it's being exposed to. It is possible to model this relationship through the Clausius-Clapeyron relationship, where if you collect data for water activity at several different temperatures for a given product, you can then use the Clausius-Clapeyron relationship to model that and then determine what the water activity would be at any temperature that you might encounter. Water activity is also related to chemical reaction rates and chemical stability. In general, as the water activity increases, the reaction rates will increase. And so these are reaction rates of things that you don't want to happen, detrimental reactions such as lipid oxidation or Maillard-Browning reactions or enzymatic reactions or vitamin degradation, hydrolysis types of reactions. All of these things will be detrimental to the product and in fact could end the shelf life. And the rates of those reactions will increase as you increase water activity. It is possible to be able to do some modeling and predict what the shelf life is going to be at a given water activity if, in fact, these chemical reactions are what end your shelf life. Because it's possible to be able to model the kinetics of those reactions as they're influenced by water activity and temperature. And temperature, many people are familiar with. You can use the Arrhenius relationship to be able to track the relationship between temperature and the rate of reactions. But that doesn't account for the water activity effect, and both temperature and water activity are having an effect on the rates. So then you can utilize what's called the Q10 and QA. Q10 is how much does the rate change with the 10-degree change in temperature. QA is how much does the rate of reaction change with a 0.1 change in water activity. And by having those values, those ratios, which are going to be specific to a given product and the reaction that's occurring, but if you know what those values are, then you can take any kind of temperature water activity combination and determine exactly what the shelf life would be or how long it's going to take for the reaction rate to be high enough such that it ends shelf life or creates the end of shelf life. And we can go in specifics again in our Water Activity 201 on how to actually do those calculations. We also have Excel sheets to do a lot of these calculations we talk about so that you only have to plug in your values and then the calculations are done for you, because we want to be able to provide tools that make it valuable to have water activity and isotherm information, and allows you to actually do some formulation and changing or engineering work on your product to make it optimal and have a maximum shelf life. So we've talked a little bit about moisture migration. Again, moisture migration is very detrimental if you don't expect it to happen. Best example that many people will be familiar with, you make your peanut butter and jelly sandwich in the morning, put the pieces of bread together, and then you store it not refrigerated. You go to eat it at lunchtime and the jam has spread into the bread, and that's because the water activity of the bread is much different than the jam. And so they're exchanging moisture, and as such, as they do exchange moisture, so the color's migrating as well, and so you can see that actually happening. So that's very detrimental. It's not something you want in a product that needs to have a long stability or shelf life. So you need to try and prevent moisture migration in any product where you're combining multiple components that could potentially have different water activities, or even processing a product so that regions of the product end up being processed to different water activities, because the water will migrate until the water activities come to equilibrium. How long that's going to take is going to be dependent on the diffusion properties of the material, and that requires some additional work to be able to figure that out. But it is possible to determine, as I'll show you in just a second, if you put two materials together at different water activities, what their final water activity will be. So here's some examples of multi-domain products. You got cereal or fruit pieces. If you take this fruit pieces in the cereal and measure the water activity of each component, they will be at the same water activity. If they process them to different water activities, then what you'll have is bran flakes that are soft and raisins that have become very hard. And that's not very desirable for a product. So it's important to have those water activities match. So they do that through the processing of the raisin and the sugar infusing of the raisins to be able to lower their water activity. So there are examples of other types of multi-domain products where you can't match the water activities. It would be impossible to do that. You would make a totally different product. So for those types of products, you have to use other strategies like packaging them in different containers, such as cheese and crackers, or like an ice cream cone that you buy in the store. It has chocolate coating on the inside that slows down or prevents the moisture migration. So those are options that you have. The best is to make the components the same water activity. If you can't do that, then try to somehow slow down the moisture migration or keep the products in separate packaging. And this is an example of how you would be able to take the information from a moisture absorption isotherm as generated by our Aqualab VSA instrument, and from that figure out, if you put two ingredients together at different water activities, what will their final water activity will be. And again, this is it's not appropriate for this seminar to go into the level of detail that's required for these equations. But again, don't get scared necessarily by the math or the equations, because we have them preloaded into an Excel sheet so that you can do those calculations. Plus, we go into much more detail about this in our next seminar. But using these models, it is possible to figure out what's going to happen ahead of time before you've ever made that product. And maybe it's okay to make it with some different water activities. That's the way you have to do it, because the equilibrium water activity is still acceptable, and that's the information that's provided by this. You can also use the isotherm to then use a static or equilibrium isotherm to figure out diffusion coefficients and calculate exactly how long it would take for the two ingredients to come to an equilibrium water activity. And here's another useful information that's provided by the moisture absorption isotherm. If you manufacture products that are in a metastable condition, are amorphous, and are metastable because they're in a glassy state that extends their shelf life for an extended amount of time, if those products move out of that glassy state into a rubbery state and experience what we call a glass transition, then their stability will go down drastically. As soon as they experience that transition, then they're much more susceptible to caking and clumping, crystallization, their texture changes, a lot of different things will happen, and their shelf life will be cut down drastically. So the strategy is to try and keep a material that's manufactured, amorphous material that's manufactured to the glassy state, is to keep it in that condition. In most cases, this glass transition is investigated through thermal techniques like DSC analysis to try and find a glass transition temperature. But we were able to find through our work looking at dynamic isotherms, and this is a method that's used in our Aqualab VSA. We've patented this method. And the advantage of this method is that you get an isotherm with very high data resolution. With a static isotherm, you may get data resolution of 0.1 water activity. With these dynamic isotherms, you get 0.01 water activity. The disadvantage is you're not doing equilibrium, so you can't do kinetics absorption. But from these isotherms, because they have such high resolution, and in a short amount of time as just a couple of days, you get these very interesting isotherms with very distinct changes or inflection points. And through research, we've been able to find that these inflection points are related to these critical transitions. And so we identified the water activity where that happens as the critical water activity at the given temperature. And the critical water activity will change with the temperature, and so there's a relationship between the two. Just like if you were to do a DSC analysis, it's important to keep the water activity constant because the glass transition temperature will be dictated by the water activity level. So from this, we've established where this inflection point occurs is the critical water activity. Why is that useful information? Well, if you're processing a product to the glassy state, very low water activity, as long as you maintain conditions through the combination of packaging and storage and where you keep the material at some water activity value below that critical value, then you know your product will have an extended shelf life. But if it moves past that critical to water activity, so higher values, or if the critical water activity moves down because of temperature and your current water activity is now higher than it, in either situation, once you move past the critical water activity, then shelf life goes down drastically, and you've created non-stable conditions for that product. And this is researchable for any type of product using our Aqualab VSA instrument to be able to generate these types of isotherms. And we've published on this. It's available out in the literature, the information about doing this work. Finally, you can use all this information once you've established through these different applications that we've talked about what an ideal water activity for your product is, whether it be for microbial spoilage, whether it be for chemical stability, whether it be for physical stability. What always comes out of that is some water activity value that you set as your specification, and we call that the critical water activity. It's the value that you have to be able to maintain or better conditions than that in order to be able to maximize the shelf life of the product. Well, if you know what that information is, the other factor that contributes heavily to shelf life is the packaging. And the purpose of the packaging is to extend shelf life, and most often by serving as a moisture barrier and sometimes as an oxygen barrier. But one of the most important properties of any packaging is its moisture barrier properties. And when you put a sample inside of a package, the resistance of the package to moisture diffusion is going to be much greater than the sample itself. And so it essentially becomes the only dictating determinant for how fast the water activity changes, and hence what the shelf life will be. So if you know what the critical water activity is through work that you've done, it's possible to take that value and plug it into some equations and figure out exactly what conductance of packaging or water vapor transmission rate you have in order to achieve a desired shelf life for your product. You can use it to figure out what the water activity will be inside of your current packaging material based on its water vapor transmission rate when it's exposed to different environmental conditions. Or you can even figure out what the water vapor transmission rate or conductance of your packaging is, if you don't already know, by some simple experiments that you can do with an environmental chamber or with an oven and some sealed desiccator chambers. Providing you valuable information about how exactly your packaging is performing. Are you over packaging? Are you under packaging? Is there ways to save costs with packaging material and still achieve your desired shelf life? So all of that's possible using these concepts of water activity, moisture absorption, isotherms. So I encourage you, if this is something that you're interested in, to tune in to our later seminars 201 and 301 to find out more specifics about that. So hopefully this seminar, that's the basics of water activity, that we've been able to, I've been able to teach you something about what water activity is, that you will know from this point on that it's a measure of the energy status of water in a system. You won't use the terms free and bound unless you're making qualifiers of what you mean, but instead water activity is the energy of water, and how much energy does water have relative to pure water. Hopefully we've been able to introduce you with different ways of being able to measure that water activity through different types of instrumentation that's available, and also investigate the relationship between water activity and moisture content through moisture absorption isotherms, and also what the difference is between water activity and moisture content, where moisture content is a quantitative measure of the amount of water, not related to microbial growth, and water activity is better correlated to all those types of things that end shelf life than moisture content. If you're going to determine some sort of measurement of moisture, and everybody knows that moisture affects shelf life, but if you want to try and really do some modeling of shelf life and figure out shelf life, you need to have water activity values and not moisture content. And so that comes back to the instrumentation, the options that are available for measuring water activity. Decagon prides itself on providing application support for our instrumentation. It's not just you buy an instrument and then you go. You're always welcome to contact us if you have specific questions. We have an applications engineer on staff. I'm always ready to help as well. We're constantly doing research on new ways to utilize our instrumentation and the numbers that come from them, as well as looking into new instruments that measure things that possibly aren't being measured at this time. And like with our new instrument, the Aqualab VSA. And I encourage you to check any of those out. They're all available, and information available on Decagon's website, or more specifically Aqualab's website at www.aqualab.com. And then just finally, water activity has many different applications for microbial safety, chemical stability, physical stability, and tune into Water Activity 201 and 301 to get more specifics about those particular subjects. And with that, that concludes our virtual seminar.